Information in images. Information is stored as a series of binary numbers, 0 or 1. One digit, 1, 0 or 1, is called a bit. Each bit doubles the number of options. For example, consider something moving a fixed distance each step. After each step, they have a choice of turning left, denoted by 0, or right, denoted by 1. So we start here, and a 1 takes us to the right, a 0 to the left, a 1 to the right, another 1 to the right, and a 0 to the left, and we end up here. So we can write this particular route as 1, 0, 1, 1, 0, and I'll write that here. For these 5 bits, there are many possible alternatives. In fact, every time we add a bit, we double the number of options. And so we can say that the number of alternatives is equal to 2 to the power of the number of bits we have. In this case we have 5 bits, so we have 2 to the power 5, which is 32 alternatives. 8 bits is known as a byte, and this gives 2 to the power 8, or 256 alternatives. Having a series of 8 bits is known as a byte, and this gives 2 to the power 8, or 256 alternatives. If we want to know how many bits are needed to store some information, we can use the formula the number of bits is equal to the log to base 2 of the number of alternatives, or I is equal to log to base 2 of n, where I is the number of bits, or the amount of information, and n the number of alternatives. So, if we needed a different binary number for each of the 101 Dalmatians, I is equal to log to the base 2 of 101, which is 6.65. So we would need 7 bits. If we needed a different binary number for each of the 60 million people in the UK, I would be log to the base 2 of 60 million, which is 25.8. So we need 26 bits. Here we have a small grey box, and you may be able to tell it is slightly darker in the bottom right hand corner than the top left hand corner. If I magnify it many times, you see it's made of many small squares, each of a particular shade of grey. These are called pixels, or picture elements. Each shade will be given a different binary number. The more bits we have available, the greater the range of shades we can have. If we have 8 bits, we could have 256 different shades of grey. Now a rainbow coloured equivalent. Just expand it. And again you see many pixels of many different colours. For a colour image, we need 3 binary numbers, one for each shade of the primary colours of light, red, green and blue. Different combinations of these shades will give many different colours. So each different shade is assigned a number. Here I've used the decimal numbers just to make it easier to follow. In reality they would be given binary numbers. I've listed here the binary equivalents for the decimal numbers 0 to 7. The amount of information in an image is equal to the number of pixels multiplied by the number of bits per pixel. So in this case we have 9 pixels and 3 bits for each pixel, which is 27 bits of information. Computers are very good at manipulating numbers, and now we have our image stored as a series of numbers. The computer can change the image by carrying out mathematical operations on these numbers. So here we have a simple stripe. By adding 2 to each pixel, we'd get an image like this, a brighter image. By multiplying each pixel by 2, we'd get something like this, increased contrast in the image. Here we have a region of mainly light shaded pixels with a dark pixel in the middle. The dark spot could be noise, unwanted information. To reduce it, we can replace that pixel with the median of itself and its neighbours. So if I list the numbers in order and pick out the median, I can then replace the central dark image, which we believe to be noise, with value 6, and you see we've successfully removed the noise from the image. If we want a particular region to stand out, we can get the computer to assign the required pixels a completely different number, and therefore colour. So here we have a faint stripe of 4 in the middle of a region of 2. What we can do is get the computer to change the 4 pixels to number 97, and then we get something like this. We've applied false colour, and the stripe really stands out. This could be used to highlight possible diseased tissue on a body scan, for instance. We can get the computer to highlight edges or changes in shading for us. If we multiply each pixel by 4, then subtract the values of the pixels above, below, left and right of it. For instance, for this pixel, we multiply 6 by 4 to give 24, then take away the value of this, this, this and this, which of course are all 6. That gives this pixel a value of 0. That would be the same for all these pixels surrounded by 6's. And so the pixels in the uniform region all become 0. If we look at the pixels along this edge, so for instance this pixel, 4 times 6 is 24, then we take away 6, 2, 6 and 6 to give a value of 4. The ones down here would be 4 times 2 is 8, minus 6, 2, 2 and 2 gives us a value of minus 4, but our lowest value is 0. So we get this effect. This highlights any edges. Of course, it would be easy to get the computer to make any edges dark and uniform areas light, if we wanted it to. This method is known as the Laplace rule. We might want to smooth an edge rather than highlight it, and if we replace each pixel by the mean of itself and its neighbours, so for example this pixel would be replaced by the mean of all these 6's, which of course would be 6. So the pixels in the uniform areas stay the same. These pixels would become shade 5. These pixels would become shade 3, and the uniform region again would stay the same. So this would give this type of effect, where the sharp edge has been smoothed.